Hi, welcome to Data Structure and Algorithm series by Coding Ally. Coding Ally is a nonprofit organization where we believe women and gender minorities should have a safe space and support system where they can foster their skills and career in tech. I'm your host, Sue. In this video, I would like to go through this problem, 160 intersections of two linked lists. This is the agenda. First, I will walk through the problem statement and then thought process behind, and then we will write the code together to implement the algorithm. So this is the problem. Given the heads of the two singly linked lists, head A and head B, return the node at which the two linked lists intersect. If the two linked lists have no intersection at all, return null. So let's have a look at this example. In here, we've got for A, we've got 1, the node A2, and then C1, and then C2, and then C3. So for B, we've got B1, and then B2, we've got B3, and then here. So from the diagram, we can see that this is the intersection, which is C1. So how can we find that intersection? So for that, let's think about the approach. So in terms of the approach, so we've got the linked list. We know that for the linked list, we need to start from the beginning of the linked list. So linked list, we will start from here. For A, we will also start from B. So from two linked list. So to find the intersection, at the start, we can see that we need to move. This here, we can see that we need to move 2 times. In here, we can see that we need to move 1, 2, 3 times. And then if the value, we have to compare the value. We have to compare the value, and if the value are the same, then we know that this is the intersection. This is the intersection. Okay, let's have a look at this example. So this is very similar to this example. So let's have a look at this example. So in here, we see that this is significant. So we've got 1, 9, 1, and then 2. And here we start 3, and then here will be 4. So this is a good example. So we know that this linked list is going to start from the beginning. So linked list is we always need to start from the head. So because we only know the head of the linked list. So we know the address. So that's how we start. So now we have to move. For this one, let's say you know A, it will be 1, 2, 3. We need to move 3 times. But for 3, we need to move only 1 time from visual observation. And we compare the value, they are equal, then we know that this is the intersection. So I want to show you another example. This is example 3. In this case, there is no intersect. We've got 2, 6, 4, and then we've got 1, 5. So in here, 2, 6, 4, keep moving, and then keep moving, get to the null. We keep moving, we get to the null. And then once we get to the null, then we will return any of the node. So from here, what can we see? From here, we can conclude that I'm going to erase or I can clear it all. So now we can come up with the approach. The approach is for each of them, let's say we are going to use example 2. So 1, 9, 1, and then 2 is the intersection. We've got 4, and then 3. So for this one, we know that we need to find the length of A. So this is the linked list A. Let's say this is the linked list B. We always start from the beginning. So we need to find the length. So step 1 is going to be find length for both A and B linked list. So this is step 1. Step 2, we have to step 2 is we need to move. So when we move, like we need to, so this is the, let's say head node A, and this is the head node B. And what we have to do is as long as this A length, if it is greater than B, which is in this case, then we have to keep moving until A is in line with B. So what I mean by that is now, if move to here, is it same? No, because the length of the A is 1, 2, 3, 4, 5. 5, and length of the B is only 3. So we have to bring two of the lengths together. So keep moving, keep moving. Now, when we keep moving, we have to decrement the length of A. So first we compare, and then we will decrement length. So that is for this case. So once that become 2, 3, the length become 3, then we know that both linked list A and linked list B has got the equal length, so 3 equal 3. In this case, we can move both of them together at the same time. And we keep comparing 3, 1, are they equal? No, keep moving. Once they got to here, then 2, it's equal to 2. So now we have find the intersection. So therefore, in step 2, if A is greater than B, we move and then decrement the length for A. And we do the same thing for B. If A length is less than B, so it means B is greater, then we have to decrement the length for B, and then we need to move forward B. So we move the node. So now in here, when they could be, we compare. The stopping condition is while the value that at the linked list, let's say head A, if it is not equal to head B, in this case, then we have to keep moving. Keep moving both linked list A, head A, and linked list B. And then by the end of it, we come back to example 3. If there is no intersection, then we can just simply return one of the head. It could be either A or it could be B. So this is the algorithm thought process behind. So now let's translate this algorithm into code. So let me move this to this side. So first, we have to find the length of both A and B. So for this, we can do it this way. So we have to find the length. So to find the length is we need to find out, let's say, length of A, and then that it's going to be initially it's 0, and then we have to keep moving until we get to the null. So we will check while, let's say, head A, if it is not equal to null, then we will keep moving. So we will move head A is equal to head A dot next, and then we will increment the length A. And then after that, we can get the final length. But instead of writing it in here, we can see the repetition for both A and B. We have to change that. So we can write a separate function. So for that one now, I'm going to write it. The end result that I want is the length for node head A and B. So therefore, I'm returning the integer type. And I'm going to give the name find length. So in here, what I am passing in is the node. And I will copy paste that. So for here, I can just change length and then length, increment the length. And then by the end of this, once we get to null, then we are, in this case, like we are at the end. So for example, we are at here, and then that will be pointing to null. So in this case, it's going to point to null. So in this case, we can return the length. So which is this. So I'm going to paste return. Yeah. So now we have write this function. So now we can just simply call this function to find the length. So for the head A linked list, I will call it A, and then it will be, I'm going to call this function find length, and into this I'm going to pass in head A. So same thing for B. B is equal to find length and then head B. So we have done the first step. So I will say find length. Find length. So that is step 1. So now we can do the step 2. For this step 2, we have to align these two. So that align means we need to align these two at the same time. So therefore, we compare the length. So that's what we will do. So in this step, compare the length and move appropriately. So for here, what we have to do is, while as long as A length is greater than B, then we have to move. So head A is equal to head A dot next. We are going to move from 1 to 9 in this case, and then we will, because we have moved, so we need to, initially it has got 1, 2, 3, 4, 5. 5. So after we move 1, so the length is going to be 4. So for that, we will need to decrement the length. So A minus minus. And we do the same thing for B. While A, if it is less than B, then in this case, then we have to move head B. So head B is equal to head B dot next, and then we need to decrement the length for B. So now that step is going to be here. So the length, after we have gone through this loop, then we are at the same length. So for here, they could be at the same value or they could be different values. So for that, we have to check if head A, if the value is not equal, it's not the same as B. So typing error, it should be A. If it is not the same as B, then we have to move both of them at the same time. So for that, head A is equal to head A dot next, and then head B is equal to head B dot next. So by the end of this iteration, then if they are the same, if we find the intersection like in this, for example, I'm going to bring it here. If we find the intersection like example 1 or either example 2, then we can just simply return it. Otherwise, then we can return either head A or B, and then the result is going to be null. So let's run the code. Okay, the length is incremented. Oh yes, it should be this and semicolon. Cannot find the symbol. Good. Because I literally copy and paste at the beginning, so I made this mistake. I should have changed to node because that is the value that I am passing in. So I will change this, and I think that should be it. Yeah, and I can submit it. So let's talk about time and space complexity. So for the time complexity, at the worst case, it will be O of n, because in example 3, as you can see, there is no intersection, and then we would have gone through every single node in A, so which is higher. So therefore, time complexity is O of 1, and space complexity is O of time complexity is O of n. Space, because we've gone through every single node, but space complexity is O of 1 because we are just simply moving the linked list node. So that is the solution for this this problem. So I'll come back to here. So thanks for watching this video. We have got fortnightly regular coding session, so please join that, and also please follow us at our social media channels. Thank you for watching.